Hi everyone, so I received a question asking, and this is 2017 past year. So let's look at the question. In a longitudinal wave produced on a horizontal spring, so you have a horizontal spring, I've drawn it out here. The coils move back and forth in the direction of the wave motion. So when we say coil, it means by we are seeing one circular loop. So one circular loop means by a coil. Okay. If the coil speed is increased, does the wave propagation speed increase, decrease, or remain the same? So they are talking about spring. Then spring is made out of a lot of coils. I coil it around to form a spring. So let me just get through this thing first. Okay. It says it's a longitudinal wave. First thing, it's a longitudinal wave. So if you know it's longitudinal wave, then the particle vibrational velocity should be parallel to the direction of propagation. So with that said, we are expecting that these coils here, okay, let me pinpoint. So these coils here will be moving back and forth, and the motion of the wave should be traveling in this direction. Okay, so you can call it longitudinal wave because the direction of the vibration is vibrating back and forth, but the motion of the wave is along the spring. So these two, they have the same, they have the parallel direction. Okay, so what I usually think is I will actually approximate this spring right into many different coils. Okay, so instead of calling it one separate one spring, I can think of it as a spring made of many circular coils. Okay, so these circular coils are somehow connected. Okay, but I approximate it as many circular coils. So if I approximate it as many circular coils, then I further approximate it. Okay, the first approximation is approximating it as circular coils. Then the second approximation that I make is I approximate it as each coil is technically one particle. So that's why if we talk about speed of the coil or coil speed, it will just be the same as the speed of the particle if we do this approximation. Okay, so from here we can say that coil speed in this case is just equivalent to particle vibrational speed. Okay, so coil speed, if we say it's equivalent to particle vibrational speed, we can change the question to be something like this. In a longitudinal wave, the particle move back and forth in the direction of wave motion. So until now, this is just general statement. Longitudinal wave, particle move back and forth in the direction of wave motion. If the particle speed is increased, does the wave propagation speed decrease, remain the same, or increase? So they're asking if this particle vibrational speed increase. So let me move down a little bit. So if particle vibrational speed increase, what will happen to the wave propagation speed? So it's either that it increase, or it decrease, or it remain the same. So particle vibrational speed and wave propagation speed are definitely different things. Even in our syllabus, we call one of them Vy for particle vibrational speed, and we call it V for wave propagation speed. Particle vibrational speed is the speed of the particle moving. Okay, speed of the motion of the particle. Whereas wave propagation speed, it's the speed of the wave pattern. So these two things are definitely different things. So if we are looking at particle vibration speed, it means that we are actually focusing on just one particle and track its change of speed with time. So when we plot this kind of graph that looks something like Vy against t, then what that graph is showing us is actually what is the speed of the particle as time changes. Okay, as time passes, what is the speed? That's a poor graph. So for instance, if you look at this point over here, it represents a time where the velocity is maximum. Whereas for this position here, it represents a moment where the velocity or the speed is 0. So if you think of it, you can think of it like this. A particle will have to be vibrating here and there and back to its original position. So if I label this as point 1, point 1 will be the point where the particle vibration having the greatest speed. So that will be at the equilibrium. This one you have to think of it as SHM. So basically the particle here is undergoing something like SHM. So for SHM, we know that the maximum speed is at its equilibrium position. So you can think of this point as 1. Then you can think of the point where Vy equals to 0 is the point where the particle reached its maximum displacement. So 2. Okay, so actually not this one should be 2, but you get what I mean. The maximum should be 0, the equilibrium should have maximum particle vibrational speed. So that is particle vibrational speed. We are looking at one single particle and tracking its speed and how it changed with time. So this is Vy against t. But wave propagation speed is we are looking at the shape of the wave traveling across the medium. So this one can be a bit difficult to explain. So if let's say you are looking at a water wave, okay, the water wave looks like this. Okay, then sometime later you still see wave, no problem, but the section that you are tracking have already moved to the right. The pattern over here, let's say I trace this point. The pattern over here has traveled by this much distance over a certain amount of time. So if you continue to track it further on, then you see that the wave pattern have already traveled to here. So you are tracking the pattern of it. Then as time passes, you see that the pattern moves across a certain distance. It's not the particle itself moving. There's no transfer of matter in a wave. It's the shape, it's the pattern moving. Okay, so the pattern moving across a distance over a certain time. So you take the distance, divide by the time, then you get the wave propagation speed. That is the speed of the wave pattern traveling across the medium. So these two things are different. So what controls this speed actually? So particle vibrational speed, we usually represent it with the formula of Vy equals to A omega cos omega t, where this cos can sometimes be sine, can sometimes be negative cos, can sometimes be negative sine. It depends on what's the initial condition of the wave. But the thing to take note is we are not usually when we say particle vibrational speed increase, we are not saying that it increase like we are not saying like this kind of increase. We are not saying this kind of increase. What kind of increase are we saying is we are saying this kind of increase. This is the kind of increase that we are seeing. So on average, the particle vibrational speed increase. So how do you cause this kind of increase? You can think of it like this. You can think of Vy maximum equals to A omega. So now you can see to have a greater particle vibrational speed, what you can do is you can either increase the amplitude or you can increase the omega, either the amplitude or the angular frequency. So you can think of it like this. Just now I say the particles is moving back and forth like this, right? So in essence, you can think of it as a particle is moving between a starting point and an ending point. No, let's just not call it start and end. You make things a bit you cause misunderstanding. Let's call this point 1 and point 2, max 1 and max 2. So this is maximum 1, this is maximum 2. So you can think of your particle vibrating as this point 2 and 2 here to be this max 1 and max 2. So what's happening is your particle will be traveling like this. Then after that, you travel back, and you travel back, something like this. Okay, so if I say you increase the A, that means you are bringing your max 1 and max 2 further away. So it means by your particle have to travel through greater distance. So if you are travel through greater distance and you want to cover it within a certain amount of time, you have to travel faster in order to cover that distance within the same amount of time. So to cover that distance, if the distance is greater, then you need greater speed when you can cover it within the same amount of time. That's why your Vy max will be increasing. Okay, another aspect that controls Vy is omega. Omega, you can think of it as being related to 2 pi f, or you can see it being related to 2 pi over period. So as the period decreases, the omega increases. So period decreases means by takes less time to finish one complete cycle. So if I tell you have 5 seconds to travel from here to here, then probably you will be jogging. The particle will be jogging. If you have 1 second only to move through this distance, then probably you'll be running. Okay, that's why the period decrease, then the omega increase. So omega increase, that's why your particle have to vibrate with a greater velocity. So by changing the amplitude or changing the angular frequency, essentially you'll be changing the particle vibrational speed. So that's for particle vibrational speed. But if we look at wave propagation speed depends on the medium only. Why do I say it depends on the medium only? Let's say, right, one simple example is when you do Doppler effect question, right? Have you ever wondered why when they tell you the speed of sound, right, they always tell you the speed of sound is 343. They always tell you it's either 343 or they tell you it's 330. Why the speed of sound has a fixed speed, but in standing wave you can see the speed can be changing in any sense possible. Okay, so the speed of sound that we use in Doppler effect is the speed of sound as they travel through air. Okay, so the air, right, you can see that the value doesn't really change much for the wave propagation speed, because the air in here, you compare it to the air in US, you compare it to the air in UK, in Greenland, in whatever place, the air is slightly different, but it is not really different that it will change the wave propagation speed. What I'm saying is air in anywhere around the earth is almost the same. Okay, it's 78% nitrogen gas, then you have 21, I can't remember all those things, but the composition of air is about the same. So if the composition is about the same, then we can say the medium is almost the same, no matter where you are. Okay, so the medium is almost the same, that's why you can see the speed of sound in air to be 343, because anywhere if you measure the speed of sound, it's about this value because we use the same medium. It's the atmospheric air. But if you look at the V of sound wave or wave traveling on a string, the wave propagation speed on a string, then you see that it's being controlled by this equation over here. So this one will be tension, and this one will be mass per unit length. So what's the issue here? So it's unlike air right now. Air in everywhere on earth, it's like almost the same. But when it comes to string, you can be stretching the string with different tension. You can have different kind of string. Some string are more massive, in your words is heavier, or some string will be lighter, some string will be made out of material, different material. So all these things are actually affecting how the wave propagates on the string, because these things are making changes to the medium. If a string is being stretched tighter, you are actually doing something to the medium. You are making the medium less flexible to vibrate. Okay, if you are making the mass greater, you are making the length of you are making the string more massive. Essentially, you are making the string more sluggish. Sluggish means, right, it's really hard to move it. So if it's really hard to move it, then it will be vibrating slower. Okay, so you are changing the medium, that's why you change the velocity of the wave propagating in the medium. So what am I trying to emphasize here is this thing, to change the wave propagation speed, you have to manipulate the medium. The only way you can change wave propagation speed is to manipulate the medium. You can't change the wave propagation speed by increasing the frequency. You can't change the wave propagation speed by decreasing the wavelength. Okay, many students like to say, v equals to f lambda, right? So if I increase f, won't the v be increasing? The thing is, it's not that it works that way. Okay, the v here is being controlled by the medium. The medium decides the v. Then once the v is being decided, then the v is like that already. Then if you increase the frequency, what actually happens is you decrease the wavelength actually. So most of the time, if you don't change the medium, then the v will be constant. Then you increase frequency, you decrease wavelength. If you decrease frequency, you increase wavelength. But the wave speed doesn't change because you don't change the medium. So that's the idea of wave propagation speed. But if you look into particle vibrational speed, the way you can change particle vibrational speed is by actually changing the wave that you create. You're changing the wave that you create. Let's say for amplitude, right? You can be swinging, you can be oscillating the string more vigorously. Okay, if you want to increase the angular frequency, what you can do is you put it on some kind of like a vibrator. Then you can change the frequency of the vibrator. Then the angular frequency will be increasing. Then essentially you are changing the particle vibrational speed. So I hope you see the pattern here. If you are talking about particle vibrational speed, you change it by controlling, by manipulating the wave being produced on the string, on the medium. But if you want to change wave propagation speed, you have to change the medium. Let's say for air, right, what you can do is you can change it to a pure helium gas, then the speed will be different. Or you can increase the temperature of the gas, making the particles vibrate more vigorously. And that is changes that you can make to the medium. But you're not changing if you change the wave produced in the medium, it will not change the wave propagation speed because you are not changing the medium. So the keyword that I want to say is one is depending on the wave produced, okay, whereas the other one is depending on the medium. So now if you look back to the question, we have still really far from it. So they say they increase the coil speed, means by they increase the particle vibrational speed. So will it cause the wave propagation speed to decrease, remain the same, or increase? So when you talk about wave propagation speed, you talk about medium. So if I increase the coil speed, do I change the medium? No. Increasing the coil speed is by increasing the amplitude or increasing the angular frequency. Changing both of these things will not change the medium that you are traveling. You are not changing the spring from steel to plastic spring. You are not stretching the spring to be tighter. You are not doing things to change the medium. What you're doing is just vibrating it faster or vibrating it more vigorously. Okay, those are changing the wave. So in that case, we can see that the wave propagation speed remain the same because there is no change to the medium. Okay, you can say increasing the coil speed. Okay, let me just write it down. I don't have the answer scheme, so this is my personal answer. So that's my explanation for this question, and I think, yeah, I've explained quite in detail the difference between vibrational speed and wave propagation speed. So that's all for this question. Thank you very much.